start recording and let me start my presentation. So, in this lecture, I want to continue to talk about power system stability, and this is continues directly from the previous lecture and further develops the fundamental concepts introduced earlier. And in this session, we want to extend the discussion on stability issues in power systems, focusing on how modern power networks respond to disturbances and maintain reliable operation under dynamic conditions. Okay. Uh, and Building on the fundamental principles already covered in my previous lectures, so this lecture aims to uh, deepen your understanding of system behavior, stability limits, and the key factors that influence secure and stable power system performance. Okay. In this slide, I want to introduce the electrical model of synchronous generators, highlighting that their electrical dynamics are inherently complex, and a detailed study of these dynamics is behind the scope of this course. However, we will focus on the simplify approach. So, especially I adopt the classical model, which captures the essential behavior of synchronous generators while keeping the analysis manageable and suitable for stability studies. Okay, this slide illustrates the concept of subtransient, transient, and synchronous reactances in a synchronous generator. It shows how the internal reactance of the machine changes depending on the time period after disturbance. Immediately after fault, the generator operates in the subtransient state with the lowest reactance x prime, second prime. So followed by the transient state with the reactance x prime. You know here you can see x prime and x second prime, and finally reaches the steady state condition characterized by the synchronous reactance xs. Okay. These relationships, x second should be less than the x prime, and is both of them are less than the xs, is fundamental in understanding the dynamic response of synchronous machines during the responses. Okay, this slide describes the time-based behavior of a synchronous generator during different operating periods following a disturbance. The system response is divided into the subtransient period, lasting only a few tens of milliseconds, the transient period, lasting a few hundreds of milliseconds, and finally the steady state conditions. So these steps reflect how electrical quantities evolve over time and gradually settle after disturbance. The classification is also consistent with mechanical transients, showing the close interaction between electrical and mechanical dynamics in power system stability analysis. Okay. This slide present the classical dynamic model of synchronous generators, which closely follows the structure of the steady state model but is adapted for transient analysis. In this representation, the synchronous reactance is replaced by the transient reactance X prime, allowing up to better capture the generator's behavior during the electromechanical disturbances. The internal voltage E prime behind X prime services as an effective approximation, making the model both simple and sufficiently accurate for studying short-term dynamic response. Okay, so this slide also explains how the classical generator model behaves under different operating conditions. When the generator is uploaded, the internal voltage E prime is equal to induced voltage E. However, under load E prime is determined by the terminal voltage VT plus the voltage drop across the transient reactance, which is equal to J X prime I. Both E and E prime represent the voltage induced in the stator by the rotor's magnetic field, while the angle delta, this delta indicates the rotor position. And importantly, this angle is consistent with the one used in the mechanical model linking electrical and mechanical dynamics. Okay, this slide shows that how the electrical and mechanical models of the generators are connected through the swing equation. The equation relates the rotor angle delta representing both electrical and mechanical position to the balance between mechanical input power Pm and the electrical output power PE. So the term involving inertia H and synchronous speed reflects this synchronous speed reflects how the rotor accelerates or decelerates in response to this power imbalance. This relationship is fundamental for analyzing generator stability and dynamic performance. Okay, this slide highlight that stability is not just a property of the generator, but of the entire power system. Let me add a new student. Okay, therefore, the generator's electromechanical model must be connected to a representation of the surrounding network. So the simplest approach is to model the rest of the system as an infinite bus behind reactance. The infinite bus acts as an idle voltage source with constant voltage magnitude, frequency, and phase angle. So let me, okay. Although this is a simplified assumption, it provides valuable insight into the key factors affecting system stability, and more detailed models can be introduced later for greater accuracy. Okay, this slide illustrates the one machine infinite bus model, a simplified representation widely used in power system stability analysis. The generator under study is modeled by its internal voltage E prime with delta angle behind the transient reactance X prime, while the transmission network is represented by an equivalent reactance X. The generator supplies current I to an infinite bus, which maintains a constant voltage V infinite with angle of the zero, regardless of the system disturbances. So the terminal voltage VT lies between the generator and the network. This model assumes that the rest of the system is very large and unaffected by the generator dynamics, allowing us to focus on rotor angle delta behavior and analyze system stability in a simplified, effective way. Okay. This slide represents the electrical power transfer equation in the one machine infinite bus model. The generated electrical power, PE, with a delta depends on the internal voltage E prime, the infinite bus voltage V infinite, and the total reactance X prime plus X between them. So the key result can be found based on this equation. This equation shows that the power output varies sinusoidally with the rotor angle delta. The maximum power transfer occurs when delta is equal to 90 degree. So sine 90 is equal to 1, highlighting the stability limit of the system. It provides a fundamental basis for analyzing rotor angle stability and understanding how disturbances affect the power system operation. Okay, this slide explains the stable and unstable operating points in the one machine infinite bus model using the power angle curve. The electrical power follows a sinusoidal relationship by using of this equation. At steady state, the mechanical input power equals the electrical output power. So we will have PM is equal to P electrical, and their intersection defines the operation or operating point. Point S at angle delta 0 is a stable equilibrium where a small disturbance results in restoring forces that bring the system back to its original condition. In contrast, we have a point U at delta U is an unstable equilibrium. Any small disturbance will cause the rotor angle to diverge, leading to losses of synchronism. Okay. And this highlights that stability depends not only on power balance but also on the slope of the power angle curve at the operating point. Okay, this slide illustrates the concept of small disturbances around operating points using the power angle curve, PE with the delta. So the intersection between the mechanical input power, PM, is a red line, and the electrical output power defines equilibrium points, this one and this one. And around the left operating point, delta left of the delta 0, a small deviation low lead to restoring behavior. So if delta increases slightly, you can see here, PE is bigger than the PM, causing the deceleration, and if delta decreases, PM is bigger than PE, so causing acceleration, so indicating a stable equilibrium. In contrast here, around the right operating point of SU, any small disturbance leads to divergence from the equilibrium, since the imbalance between PM and PE amplifies the deviation. So this demonstrates the difference between stable and unstable operating points in power system under small signal disturbances. Okay, this slide summarizes the stability characteristics of operating points on the power angle curve. any operating point delta with delta less than the 90 degree lies on the rising portion of PE and is stable because small deviations produce restoring forces that bring the system back to equilibrium. In contrast, here, any point u with the delta bigger than the 90 lies on decreasing portion of the curve and is unstable as a small disturbances cause the system to move further away from equilibrium. So it will be more unstable. So it is important to note that this stability criterion is valid only for small disturbances where linearization around the operating point is can be applied, is applicable. Okay, this slide presents the concept of the steady state stability limit based on the power angle curve PE delta. The maximum transformable electrical power curves at delta is equal to 90, which defines the theoretical stability limit. However, in practice, generators are operated well below this point, typically with delta much less than the 90 degree within the normal operating zone. And this conservation operation ensures sufficient stability margin so that in the event of large disturbances such as faults, the systems can maintain synchronism and avoid instability. Okay, this slide illustrates the power angle relationship of synchronous generator under transient conditions. The electrical output power PE with the delta varies sinusoidally with the rotor angle delta, while the mechanical input power PM is constant. The intersection points of these two curves define the operating conditions. The left intersection S represent the stable um, equilibrium point where small disturbances are naturally corrected, and the right intersection U indicates the unstable equilibrium point where any disturbance lead to losses of synchronism. Sorry, let me add a new student. Okay, this figure also highlights how stability depends on maintaining operation near the stable rotor angle delta zero, well below the maximum power point at 90 degree. Okay, this slide presents the numerical solution for determining the rotor angle at the stable and unstable operating points of the synchronous generator. First, the apparent power and power factor are used to compute the current phasor, and then the internal voltage E prime is obtained using the generator equations. From this, the initial rotor angle is found as delta is equal to 14.6 degree. Uh, okay, so this angle corresponds to the stable operating point where the system can maintain synchronism under small disturbances. So due to the symmetry of the power angle curve, the unstable operating point is given by delta U is equal to 180 minus delta zero, so is equal to 165.4 degree. So this larger angle represents the unstable equilibrium where any disturbance will cause the generator to lose its stability. So the slide clearly demonstrates how both operating points are derived and highlights the importance of operating near the stable region. Okay, sorry, 1 minute. So this slide introduces the simplest scenario for analyzing the large disturbance in power system. Sorry. And a synchronous generator supplies power to an infinite bus through the single transmission line with reactance X. Um, a severe disturbance is created by a bolted three-phase fault occurring near circuit breaker CB1, which drastically reduces the electrical output power. The fault is then cleared by opening CB1, altering the system configuration. During this entire process, the mechanical input power PM is assumed constant, leading to an imbalance between the mechanical and electrical power. This imbalance drives changes in the rotor angle and speed, forming the basis for studying the electrochemical dynamics and transient stability of the generator under large disturbances. Okay, this slide presents the simplest representation of a large disturbance in a power system, typically a fault occurring between a generator and an infinite bus. Under pre-fault conditions, the system operates in a steady state where mechanical power equals electrical power, and the initial rotor angle delta zero is determined by the power angle equation. When the fault occurs, the electrical output power drops to zero, causing an imbalance that accelerates the rotor. After the fault is clear, the system transitions to post-fault conditions where electrical power is restored but no longer equal to mechanical input, leading to rotor angle oscillations. So this forms the basis for transient stability analysis. So this slide illustrates the power angle curve used to explain transient stability during a large disturbance during using the equal area criterion. Initially, the system operates at point S where mechanical power equals electrical power. When a fault occurs in point at point S, when a fault occurs, the electrical power drops to zero. You can see the red line, and the rotor accelerates from A to B, increasing the rotor angle to the clearing angle delta clear. So after the fault is clear, electrical power is restored and exceeds mechanical input, causing deceleration as the system moves from C toward the D from 2 here. So the kinetic energy gain during acceleration is gradually dissipated, and if the decelerating area is sufficient, the rotor returns toward a stable operating point. Otherwise, instability occurs if the angle exceeds the critical limit delta LIM, delta lim. So this slide demonstrates an unstable condition using the equal area criterion in transient stability analysis. After the fault, the rotor accelerates from point A to B as electrical power drops to zero. Once the fault is clear at delta clear, the system enters the deceleration phase. However, the kinetic energy gain during acceleration is too large to be fully observed. As a result, the rotor continues past point U, which represents the unstable equilibrium. Since the decelerating area is insufficient compared to the accelerating area, the rotor angle delta keeps increasing, leading to losses of synchronism and system instability. Okay, this slide uses a simple marble analogy to illustrate the concept of acceleration under the influence of gravity. So when the marble is released from a higher point on the curved surface, it naturally begins to move downward due to the gravitational force. As it travels along the slope, its speed increases, demonstrating how gravity causes acceleration in the direction of motion. So this analogy helps visualize how objects gain kinetic energy as they move from higher to lower potential energy levels. So this slide continues the marble analogy by showing the motion after marble reaches the lowest point. So at the bottom, the marble has gained maximum speed due to pure acceleration. So as it begins to move upfield, so the direction of acceleration opposes its motion, effectively becoming negative and slowing the marble down. So, however, the marble does not stop immediately because it has already built up momentum, allowing it to continue moving upward until its kinetic energies gradually reduce. So let me the new student. Okay, this slide illustrates the stable case using the marble analogy. As the marble moves upfield after passing the lowest point, it gradually loses its momentum and eventually comes to a stop before reaching the top of the next hill. So at this instant, its speed becomes zero due to gravity. The marble then reverses direction and starts rolling back downward toward the equilibrium position, demonstrating a stable condition where the system naturally returns after a small disturbance. So this slide illustrates the stable operating condition using the marble analogy. When the marble is placed in a valley, it naturally settles at the lowest point because friction or damping gradually dissipates all the kinetic energy gain during its motion. As a result, the system returns to equilibrium after any small disturbance. However, it is important to note that the simplified power system model shown here neglected damping effects, meaning that in reality, additional mechanisms are required to accurately represent how oscillations decay and stability is achieved. Okay, this slide demonstrates the unstable case using the marble analogy again. Here, the marble reaches the top of the hill with remaining momentum. So instead of sitting, it continues moving and begins to accelerate again as it descends on the other side. This indicates that the equilibrium point is unstable. Any small disturbance causes the system to move further away rather than returning to its original position. So in power system, this behavior represents losses of stability where the system cannot maintain synchronism after disturbances. Okay, this slide present the simplest illustration of a large disturbance using the power angle curve. Initially, the system operates at point S where mechanical power equals electrical power. After a disturbance, the rotor angle increases as the accelerating power becomes positive, moving toward point C. Once the fault is clear at delta clear, the system begins to uh, uh, decelerate as electrical power exceeds mechanical point input. So stability is maintained if the rotor angle does not exceed the critical limit delta U. In other words, the maximum excursion delta limit, delta lim, must remain less than or equal to delta U. So this reflects the equal area criterion, where the accelerating and decelerating areas must balance to ensure the system returns to a stable operating conditions. So this slide introduced the equal area criterion as a simple and intuitive way to assess transient stability. During the fault, the generator accelerates because mechanical input exceeds electrical output, leading to an accumulation of kinetic energy. After the fault is clear, the generator begins to decelerate and attempts to return this stored energy back to the system. The key question is whether it can shed enough kinetic energy before reaching the unstable equilibrium point or not. The the equal area criterion provides a visual and analytical method to evaluate this by comparing accelerating and decelerating energy areas, helping to identify the main factors that influence system stability. So this slide introduces the equal area criterion starting from the generator swing equation, which relates rotor dynamics to the difference between mechanical input power and electrical output power. So we will have this equation. We already saw this equation before in my previous lecture. So by assuming the per unit speed, W per unit speed is equal to 1, the equation can be simplified, highlighting that even small speed deviations can cause significant changes in the rotor angle delta, and the equation is then integrated between two arbitrary rotor angles, transforming the dynamic equation into an energy balance form. So this leads to the fundamental idea of the equal area criterion. The system remains stable if the accelerating energy equals the decelerating energy over the swing, which can be evaluated graphically using power angle curves. This slide shows how the equal area criterion can be interpreted in terms of kinetic energy of the generator rotor. Starting from the integrated swing equation, the variables are rearranged by swapping d delta and dw, allowing integration with respect to speed instead of rotor angle. By using the relationship between the angular speed and rotor angle, the left-hand side becomes proportional to the change in kinetic energy. So we can write this one. This is a proportionally depend to the kinetic energy. So this final expression clearly shows that the difference between mechanical and electrical power here, um, integrated over the rotor angle, equals the change in kinetic energy of the machines. And therefore, system stability can be assessed by comparing accelerating and decelerating energy areas, reinforcing the physical meaning of the equal area criterion. This slide emphasizes the physical interpretation of the equal area criterion by linking it directly to the generator's kinetic energy. It shows that the change in kinetic energy of the rotor expressed in terms of speed variation is equal to the integral of the difference between mechanical input power and electrical output power over the rotor angle. So we will have this equation. So both sides of the equation represent the same physical quantity. The change in kinetic energy, you can see both of sides of this equation, showing the change in kinetic energy.